do really important things. They're short chain amino acids. If you would explain how it does what it does, you have to look at the amino acids and how they were put together. So we call those peptides or polypeptides, short chains. As you add to the number of amino acids being put on this growing chain, you begin to form what are called proteins. And the proteins that you make, depending on the amino acids that are present on them, will go through a system that will create predictable turns and folds. I want to show you some of those. We say that a long chain of amino acids has a primary structure. That is just a listing of the amino acids. It does not explain function. As the protein moves toward its functional abilities, it will begin to fold and twist and turn. And they normally do so in predictable ways, which is why there's some standards here. As the protein begins to fold and take on functional capacity, we say that it has secondary structure. And those secondary structures exist normally in this helical pattern or in this folded, pleated sheet pattern. And I'm not going to ask you to explain the differences. These are very important processes in moving a protein toward its functional nature. There are proteins that have pleated sheet folding or out the helical folding, and they're functional proteins. They are the least complicated. Now, beyond the secondary structure of a protein, some proteins will fold up into a more complicated ball of amino acids. That's Wade Warren term, a ball of amino acids. And so this yellow line here is intended to illustrate for you the chain of amino acids. This protein, in its balled up form, caused by the amino acids that are on it, has what we call tertiary structure. And tertiary structure is some of the most complicated. Explaining why this thing folds where it does is very complicated. And you think, well, why should I care? That's a fair question. Why should I care how it folds? Well, let me give you one example, because this is an example here of hemoglobin. Hemoglobin is a large protein, well over 400 amino acids in a hemoglobin molecule. And hemoglobin, as most of you know, carries oxygen around your body. Well, as it turns out, if you substitute one amino acid, if there is one amino acid out of place on this guy, one amino acid is added, two amino acids are added, 3, 4, 5. The sixth one that gets added is wrong. 7, 8, and you work your way up to over 400. You put the wrong one in the sixth position. That creates a condition called sickle cell anemia. You see what I mean? By the amino acids have to go in the right place. It's critical where they go. So tertiary structure begins to explain things for us. When you move from tertiary to quaternary structure, essentially what you're doing is you are combining proteins that have tertiary structure together into a new protein that has even more complexity. The hemoglobin protein has 4 tertiary proteins, 1, 2, 3, 4 tertiary proteins linked together to form one massive functional protein. And we say it has quaternary structure, the most complicated protein structure is quaternary structure. So here's where you went. Amino acids join together, make dipeptides. You put a few of them together, you make a peptide or a polypeptide. As the thing grows, it can begin to fold into functional configurations. We say at that point it has secondary structure, and the most common ones are the alpha helix and the beta pleated sheet. As the protein gets bigger and begins to fold up into a ball, we say it has tertiary structure. Very complicated structures. Does it matter how the tertiary structure is made? Does it make any difference? You bet it does. And some proteins, like hemoglobin, are multiple tertiary proteins put together to form one. So as we begin to talk about functional things in human physiology, and we talk about proteins, this is what I mean. Wherever we go, the nature of the protein is going to explain the human anatomy and physiology that we are most interested in. When we get to cells, next class period, we're going to say the proteins in the cell membrane explain what the cell can do. The proteins inside the cell tell me what the cell is capable of. When I move from there to the tissues, I'm going to say the way we define this tissue is based on the protein content. When I move into bones, I'm going to talk about the nature of the bone itself, made up of almost 45% protein, collagen. And so everywhere we go in this class is going to be a continuing story that I started here today with protein structure. I won't be able to explain anything to you about anatomy or physiology without talking about the proteins. Now, my job on Friday is this. So I'm going to ask you to do something for me. My job on Friday is to teach you how you make a protein. Now, my daughter took this in high school. I saw it as she learned it. But if I say words like transcription and translation to you, and that means nothing to you, it would be a really good idea for you to do a little reading before Friday's class. Because otherwise, things are going to get sticky in here on Friday. Okay, those of you who need me to stay behind, and I'll help you.